Hello students, again I am going to explain theorem that says the bounded function f defined on a measurable set E of finite measure is Lebesgue integrable if and only if f is measurable. So in the proof first part, let f be Lebesgue integrable over E. So by definition of Lebesgue integral, infimum means infimum of simple functions is same as that supremum of simple functions integral. That means lower Lebesgue integral is same as that upper Lebesgue integral, and say it is I. Right? And here these are phi and psi, both are simple functions such that f is less than equal to psi and greater than equal to phi. Given any integer n, there exist simple functions phi n and psi n such that our fx is lying between phi n and psi n and satisfying these inequality. Now how? Just see, infimum of all these integral is I. So clearly for any n, integral of psi n will be less than infimum plus epsilon. So whenever we add some number in the infimum, we are having some integral which is less than this. Same way, by the definition of supremum, if we subtract some positive number, it will not supremum. So we are having some integral which is greater than I minus 1 by 2n. So here we choose epsilon to be 1 by 2n, and when we subtract these two inequalities, we will having integral of psi n minus integral of phi n is less than 1 by n. Now we define the functions psi star and phi star. Psi star is the infimum of all these psi n and phi star is a supremum. Since we know that simple functions are always measurable, so each phi n and psi n is measurable. Again, max of 2, minimum of 2, supremum of the sequence of functions, all are measurable. So phi star and psi star, they are also measurable functions. And they also satisfy this inequality because this inequality holds for each n. So this is true for supremum and infimum also. Now corresponding to these sets, we first define delta set, then delta nu, then delta nu n. Delta set is a set of all those x belonging to E where phi star x is strictly less than psi star x. Right? So it is a set of all those x belonging to E where this inequality holds. Now delta nu, it is a set of all those x belonging to E where phi star x is less than psi star x minus 1 by nu. Right? So this delta nu depends on nu. If we take nu to be 1, it is a set of all those x belonging to E where phi star is strictly less than psi star minus 1. We take nu to be 2, so we get this is minus half and so on. Right? And the third set delta nu n, which is the set of all those x belonging to E where phi nx is less than psi nx minus 1 by nu. So here this set, it depends on n also. Here we are having infimum and supremums, and here we are having all those points from E where each phi nx is less than psi nx minus 1 over nu. Now these are some observations. A part. Now clearly delta nu, when you take the union of these delta nu's, we get delta. Okay, so when nu is very large, this is nothing but having all those x belonging to E where phi star is strictly, right? So delta is the union of delta nu. Okay, second observation is delta nu is a subset of delta nu n. Now why? Here we are having only infimum and supremum functions, but here we are having all functions phi n and psi n. So this inequality is true for each n, and here are more points of domain which satisfy this thing, and here are less points which satisfy for only infimum and supremum. So clearly this is a subset of this, right? And the third observation is that measure of delta nu n set is less than nu by n. Why? Let if possible this is greater than equal to nu by n. Then we have to take the integral of psi n and phi n over this delta nu n set. Okay, we can combine these two because these are elementary functions. We can write integral of psi n minus phi nx over the set delta nu n. Now what is delta nu n set? This is a set of all those x belonging to E where phi nx is less than psi nx minus 1 by nu, right? So we can take phi nx to be this side. We get all those x belonging to E where psi nx minus phi nx is greater than 1 by nu. We can take nu to be this side. Okay, so we can substitute this value over here. So this is greater than 1 by nu. So we left with 1 integral of 1 over the delta nu n set, okay, which is greater than equal to 1 by n. Why it is 1 by n? Now you substitute the value of measure of delta nu by n, which is greater than equal to nu by n, which is our assumption. So substitute over here, our nu will be cancelled. We will get this is greater than equal to 1 by n. But this contradicts the inequality 1. This says integral of psi over the whole set E minus integral of phi over the whole set E is less than 1 by n. However, for any subset, we are having this is greater than equal to 1 by n. So which this contradicts 1. So that means our assumption is wrong. What is our assumption? That measure of delta nu n is greater than equal to nu by n. So it means measure of delta nu n should be less than nu by n. Okay. Now from the B observation, since delta nu is a subset of delta nu n, to clearly measure of delta nu is less than equal to measure of delta nu comma n, and measure of delta nu n is less than nu by n. Okay, now our left side measure of delta nu, it is independent of n, so this is true for each n. So measure of delta nu is always less than nu by n means it is true for n tending to infinity also. So we get measure of delta nu is nothing but 0, right? Since measure of delta nu is 0, then using A, the measure of delta is 0 because it is summation of measure of delta nu's. Since each delta nu has measure 0, so measure of delta will be 0. Now if measure of delta is 0, so what is our delta set? It is x belonging to E such that phi star is less than psi star. If this set is having measure 0, it means our phi star should be greater than equal to psi star almost everywhere, right? So we get the phi star is greater than equal to psi star almost everywhere. But from here we are having phi star is less than equal to psi star, right? So this implies they are same almost everywhere. Now since these functions are measurable because they are simple functions, so f is also measurable, and this we have to prove. So whenever f is Lebesgue integrable, bounded and defined on measurable set with finite measure, f is measurable. On the other hand, assume that f is measurable function on E. Suppose f is bounded by m. So now in the converse part, what is given to us? That given that f is bounded measurable function on a measurable set E with finite measure, and we want to show f is Lebesgue integrable, right? Now what is given to us? It is bounded. So say it is bounded by m. So that means the whole values of f lying between minus m and plus m. So this will become the interval for this function. Now divide this interval into two unequal parts and consider the sets ek. Now what is set ek? It is a set of all those points from E where fx satisfies this condition, that fx is lying between m by n k minus 1 and m by n k, where our k is varying from minus n to n, right? Minus n to n means two unequal parts. Okay, so when you take k to be 0, it is a set of all those x belonging to E where our fx is lying between minus m by n to 0. Whenever k is 1, it is all those x belonging to E where fx is lying between 0 to m by n, and so on. So clearly Ek is a countable collection of pairwise disjoint measurable sets such that their union is E. Therefore, measure of E is summation k varying from minus n to n, measure of Ek. Why equality holds over here? Because all these sets are disjoint. So this satisfies additive property. For each n, we define simple functions psi n and phi n as this. Now how to define psi n and phi n? We have to define phi n and sin n in such a way that it satisfies this condition. Right? Now just see from the previous slide. Now just see as in the previous slide, we have defined the sets Ek, which is nothing but set of all those x belonging to E where fx is lying between m by n times k and m by n times k minus 1. So from here we have chosen these simple functions. Okay, so we choose psi n as this much and phi n as this much. Okay, so clearly our fx is lying between phi n and psi n. Now you take integral to both sides. Right, integral of this, integral of this. What is our Lebesgue integral? That is, upper Lebesgue integral is what? Infimum of all these simple functions which are greater than equals to f. Right, so infimum will be less than equal to any integral. Substitute the value of psi n x over here. This is nothing but m by n summation k, and characteristic function over Ek after taking the integral will be replaced by measure of Ek. Now why? What is the value of characteristic function over Ek? This value is 1 when x belongs to Ek, otherwise it is 0. So when you integrate this over Ek, its value is 1. So we get only the measure of Ek. Okay, so in case of integral, characteristic function will be replaced with the measure. Same for supremum of phi x, where phi is the simple function such that phi is less than equal to f. Okay, so we are having this value. Now you subtract these two integrals. So we will get this inequality that it should be less than equal to m by n summation k varying from minus n to n k measure of Ek minus k minus 1 measure of Ek, which is measure of Ek. Now what is this summation? This is nothing but measure of E. So we can substitute this value, that measure of E over here, right? So we having this inequality, that's infimum of all the simple functions greater than equal to f, integral of psi minus supremum of all the simple function phi less than equal to f, integral of phi is less than equal to m by n into measure of E. Since m is finite, measure of E is finite, and our left hand side is independent of n, therefore by taking n tending to infinity we will having this value is 0. So this integral is less than equal to 0. Now also we know that upper minus lower is greater than equals to 0. So this number should be equal to 0. That means upper Lebesgue integral is same as that lower Lebesgue integral. So this implies our function is Lebesgue integrable over E. Okay, so this theorem is very important theorem because it gives us the connection between integrability and measurability. Okay, this is also important from point of view, right? Now the next, comparison of Riemann integral and Lebesgue integral. We already know that Lebesgue integral is the generalization of Riemann integral, right? So in this section, we will prove that every Riemann integrable function is Lebesgue integral, but converse may not be true. Okay, so what is given to us? Let f be a bounded function defined on the closed interval ab, and if f is Riemann integrable, then this implies this is Lebesgue integrable. You can prove it by yourself. Since we know that f is Riemann integrable over ab, so by definition of Riemann integral, we are having phi1 and psi1, the step functions, such that this thing holds. That upper Riemann integral is same as that lower Riemann integral in terms of step functions. Okay, but we know that every step function is simple. Okay, so therefore we can replace phi1 and psi1 with the simple functions. Again this inequality holds. Again these equalities holds. So this will become the upper Lebesgue integral. This will become the lower Lebesgue integral. Both are same. So that means our function is Lebesgue integrable. Right? So we are having this theorem which says whenever our function is bounded, defined on AB and Riemann integrable, then clearly it is Lebesgue integrable. Right? But it is not true for every bounded function. Okay, for example, consider this Dirichlet function going from 0 1 to r by fx is 1 when x is rational, 0 when x is irrational. Then clearly our function is bounded function, clearly our function is measurable. You can prove it by yourself that this is function is measurable function. You choose any alpha and then you can show, right, that this function is measurable also. So clearly it is Lebesgue integrable by that theorem that says whenever our function is bounded, defined on a measurable set with finite measure and measurable, then it is Lebesgue integrable, right? And you can also find its integral value. That is what integral of f is equal to integral of 1 over rational plus integral of 0 over irrational. Integral of 1 means 1 into measure of rational. What is measure of rational? Measure of rational is 0. The measure of every countable set is 0. So 1 into 0 is 0 plus 0 into measure of irrational. Measure of irrational over this interval is 1. So 0 into 1 is again 0. So we will get the measure of fx, integral of fx over the 0 1 is 0. Clearly this function is Lebesgue integrable. However, this is not Riemann integrable since upper Riemann integral is 1 and lower Riemann integral is 0. So we have observed that bounded function defined on an interval may be Lebesgue integrable without being Riemann integrable. Okay. On the other hand, if your function is Riemann integrable, then it is Lebesgue integrable also. Okay, so that means the class of Lebesgue integrable function is wider than that of Riemann integrable function. However, this is not true in the case of improper Riemann integral. There may exist improper Riemann integrable functions which are not Lebesgue integrable. So now the problem 1, you can prove it by yourself. Prove that a Riemann integrable function defined on closed interval AB is measurable. You can use previous two theorems and you can prove this problem. Now I come to the next topic, which is the properties of Lebesgue integral for bounded measurable functions. This says let f and g be bounded measurable functions defined on a set E of finite measure. Then the integral of AF over E is same as that A times integral of F over E. And this is true for every real number A, that we can take constant to be outside. Now see the proof. When you take A to be 0, AF is 0. Here it is 0, so your left hand side is same as that right hand side. Okay, so for a equal to 0, our result holds trivially. So we assume that a is non-zero number, and first we assume that a is positive number. Okay, so now we consider psi a simple function, then clearly constant times psi is also simple, and same way converse. Okay, so we first consider this left hand side, a times f integral over e. It will be what? It is an infimum of all those a psi greater than equal to af of this a psi over e. Since a is non-zero and positive number, we can cancel out this both sides. And this is elementary function. We can take a to be outside. Now this is a times infimum of this. This is what? This is nothing but upper Lebesgue integral of f. Since our f is integrable, so this is same as that integral of f. Now why our f is integrable? Since it is given that f is bounded measurable function defined on a measurable set E with finite measure. So by using that theorem, measurable function bounded on a finite measure implies integration. So this is integrable. Okay, so we get integral of AF over E is nothing A times integral of F over E. Similarly, whenever you take A to be negative, you can consider A psi functions. Now when you cancel A from here, since A is negative, our inequality will change and infimum will be replaced by supremum. Rest is same. You can take A to be outside from the elementary integral. This psi is nothing but a constant function. You can take A to be outside. Okay, so this is nothing but your integral of f over e. So this is a proof of A part. Now the proof of B property, which says integral of the sum of two functions is nothing integral of f plus integral of g over e. For this we consider two simple functions such that one function is greater than equal to f, other function is greater than equal to g. Then clearly their sum is also simple function satisfying psi 1 plus psi 2 is greater than equal to f plus g. Right? So now we consider integral of f plus g over e. This is less than equal to integral of psi 1 plus psi 2 over e, which is equal to integral of psi 1 over e plus integral of psi 2 over e. Why this thing hold? Because this is elementary function. These are constant functions, right? Over the set E, we can separate them, right? Now this inequality holds for each psi 1 and psi 2. So this is also hold for infimums, right? So we get integral of f plus g over e is less than equal to integral of f plus integral of g, right? Because this is nothing but integral of f over e. This is nothing but integral of g over e. This is upper Lebesgue, this is upper Lebesgue integral g, right? And functions are integrable, so that is same as that integral of f integral of g. Okay. Similarly, consider the simple functions phi 1 and phi 2 which are less than f and g. Then their sum is also, right? Consider this integral. Now this time it will be greater than equals to this. Now why this is greater? Because this is the supremum of all these functions. The supremum will be greater than equals to. The same way here it is less than. Why? Because this is the infimum of all these functions, so this should be less than, right? So now again same, we can separate them, and since this inequality holds for each phi 1 and phi 2, so we can take supremum to both sides. We will get this thing. So from here and here we are having these two are same. So this is the proof of B part. Now the C part says if f is equal to g almost everywhere, f is equal to g almost everywhere, means f minus g is 0 almost everywhere, we have to show that integral of f is equal to integral of g over here. Means f minus g integral is 0. We want to show this thing. Again, Same reason we consider simple function psi, which is greater than equal to f minus g, right? Then since f minus g is 0 almost everywhere, so we get psi is greater than equal to 0 almost everywhere. Then clearly integral is greater than equal to 0. And this is true for every simple function such that psi is greater than equal to f minus g. So this is true for infimum also. So when you take infimum, this is nothing but the integral of f minus g. Similarly, we can prove the reverse inequality by considering again a simple function phi which is less than equal to f minus g. Okay, so this proves the result. When you combine these two inequalities, we get this is nothing but 0. This is we want to prove. Same way, you can prove the D and E part. The D part says whenever f is less than equal to g almost everywhere, integral of f is less than equal to integral of g. Same way, using C, you can prove this thing. So you do it by yourself. Also the E part that says whenever a function lying between some fixed numbers, integral of f is lying between alpha times measure of E and beta times measure of g. Now why this thing hold? Using ABC part, integral, we take integral to both sides, that alpha is less than equal to f is less than equal to beta. Take integral, we get alpha into integral of 1, which is measure of E, right, is less than equal to integral of f is less than equal to beta into integral of 1, which is again measure of E. Okay, so with this E part hold, and similarly you can prove the f part, that integral of f over E1 union E2 is the integral of f over E1 plus integral of f over E2, where E1 and E2 are disjoint measurable sets. Okay, so we can separate them. So with this, all the properties of integrable functions, bounded integrable functions, are proved. Okay, thanks.